okay, just to be clear on what I was saying for the time constant, okay? The time constant is a value when you're dealing with RL, RC, RLC circuits. Okay, is a value, is a number, and you denote it by tau. It's denoted by tau, time constant. And its unit is in seconds. Okay, we can actually get into proving this. We'll get into proving this. All right, its tau and its unit in seconds. So what is the time constant? Is the time it's taking for the initial value. So for I naught. So is the time it takes for I or V to reduce by 36.8% of its original value. That's what time constant is. So usually when you have your graph, that looks something like this, alright? And it's always look like this, the decaying exponential. Alright, let's say this is V naught. So let's say this is here, or at this point, this arbitrary points. This time is is where this voltage value is 36.8% less than the original value V naught. Then this becomes our time constant, tau. Alright, so that's what the time constant is towards. It's the time it takes for, like I said, the time it takes for the value to reduce by 36.8%. So what is it for circuits? For RC circuits, your time constant tau is equal to R times C, units in seconds. Alright, for RL circuits, your time constant is L over R. Units are still seconds. And you've got to be being careful, particularly with RL, because while deriving, you may end up with R over L at some point. While deriving, you will have R over L at some point, but the end goal is to get it to be T over time constant. I'm going to explain what I mean. So for RC source free, okay, remember our value, our formula, voltage as a function of time is equal to V naught times e to the minus T over RC volts. Okay, so what happens when we sub time constant in? It becomes V naught e to the minus T over tau volts. Alright, so we can see our formula is much cleaner than it was at the beginning. The same thing is going to happen for RL. But we've got to be careful not to make a mistake. I of t is going to be I naught e to the minus R over L. Let me do this. R times T all over L amps. Okay, so remember we said time constant is L over R. So that means our final formula is going to be T over tau. So we're still going to have the same T over tau, T over tau, T over tau, T over tau, alright? So that's I naught e to the minus T over tau amps. So that's what we try to get when we're dealing with RC and RO circuits. So let me see for a bonus to try and explain why units for time constant is seconds. So this will be in two parts actually, for RC and for RL. Alright, so for RC, remember our time constant tau is R times C. Alright, so from Ohm's law, remember I said B is equal to IR. So R is V over I. So the dimensions for R are going to be that for voltage over that of currents. Okay, I'm going to make an important distinction here. Current is charge flowing divided by time, Q over T, dQ dt. Alright, so we can say that the dimensions for current is dQ over dt. Alright, so just keep that in mind. So we can throw this back into here and say that the dimensions for resistance R is V over I, so that's that of voltage, that of dt over that of dq. Okay, so let's move on. T is RC, so this is cool, it's really fun. So remember, what do we get for R? V, unit for voltage is volts, so let's keep it in the brackets as volts times time is seconds, alright? So seconds over Q is charge. So how do you measure charge? Coulombs. let me keep it as Q so we won't get confused with capacitance. So Q is for charge. Let's take note. Alright, so we're going to remember, wait, but what is capacitance? Our formula for capacitance is Q is CV. Alright, so this is charge, this is the capacitance, this is the voltage. Capacitance is the charge per unit voltage. Alright, so if we're to make C the subject of formula, we'll end up with C being Q over V. Alright, so let's throw this back in. So tau is, remember what we go for R, V times seconds over charge times Q over V, Q over V. I didn't even need to use dimensions. I could have just used the quantities as they were. Alright, so as you can see, Q cancels out, voltage cancels out, and we know that the dimensions for our time constant for RC circuits is in seconds. Alright, fantastic. But for RL, same thing, but a little bit funkier, sort of, kind of. Remember, for time, our time constant is L over R. Alright, our time constant is L over R. So from Ohm's law, I is V over R. So R is V over I. So the dimensions for R is going to be voltage over current, right? This is I, pardon me. Alright, but for L, remember we said L is the voltage through an inductor is L di dt. Alright, so since V is L di dt, let's see if we can make L the subject of formula. So that's going to be V dt over di is going to equal L. Alright, so let us fantastically throw this into our formula for time constant. Alright, so time tau is L, so that's V dt over di as voltage times dt, that's seconds. Alright, over di, let's call that charge, just leave that as I, okay? Times, remember we're dividing by R, so whatever we get for R, make this inverse. So that means I will come up, V will go down, times I over V. Alright, so very evidently this cancels out, and we end up showing that the dimensions of tau, the time constant for RL circuits, is seconds. Alright, so hope you've been able to, hope this was much help. And in the next videos we solve questions from source free RL and RC, then get to step response, then get to RLC and move on that way.